Hello, welcome back to another episode of a Kitchen Table Coder. So all we're doing at the moment is taking a look at Rust. This will be episode 02, and if you've seen the previous episodes, you'll know that I'm going through the Rust programming book. And the convenient thing about this is the book itself. If you go to the Rust language site, they actually have the book online, so you don't actually even have to buy it. And so the reason why I wanted to come in here is just to talk about what this episode's going to cover. So we're up to basically chapter 3 now. Episode 0 was basically just getting started, setting up the environment. Episode 01 was this programming and guessing game, where it sort of goes through the process of putting together a guessing game program, and just to sort of introduce you to some broad concepts in the language, which is what I did last week. And then this week I'm going to just do a section within this third chapter. So in episode 02, we're going to really cover variables and mutability, data types, and I'll talk a little about comments. There's not really much to say about comments. Up and coming episodes, I'm very much tempted to break this down so that I do an episode on functions and an episode on control flow. And the reason why that is, and I do apologise up front that this is going to take a number of weeks to get through. I just really need to spend time up front walking through the different sections, hand typing it myself, so I sort of build up knowledge through just doing that, not so much muscle memory, but just interacting with the code physically rather than just copy pasting it from here, which is what I could do. And I'm finding I'm picking up things a lot better by doing that. So there might be a situation arises where I might push out 2 episodes a week on the same day, but at the moment I'm just going to try and base it down into manageable chunks, just for my learning here. So that's where we are going to be today, if you are indeed learning to code this way, because I do know that some people are just using these videos probably for the ASMR qualities, which is fine. But if you aren't, and you're actually genuinely using it as a way of getting into Rust programming, then that's what we're going to be looking at, is variables, immutability, data types, and I will talk a little bit about comments as well. The other thing is, I don't follow through in exact order that it's presented in the book, either the book or the website, which I think are identical, and that's just for convenience when I'm putting the code out. So we're in Visual Studio Code. I'm going to set up a new container for this. I'm just going to call it variables. So we're going to go cargo new variables. There's our container. Again, if we go in under our files, under our user files, what we should find is under the Rust user, under projects, the new folder variables. So because obviously I ran this cargo command inside of projects, the variables folder will be created in there. So just to recap, we've got our cargo TOML file, which we won't be altering today. This is pretty straightforward. We haven't got to introduce anything that's not part of the standard library, that's not already in that initial container, if you like, initial environment. And then we've got source, and we've got our main file here. Now you've probably seen here, I'm ready to go. So we're going to copy this in to save me embarrassing myself with my slow on-screen typing. And go into here. Currently that main file, when you create a new package, as you've seen previously, just contains like a hello world program. So let's open the file. It was the last episode, so here we go. There we have it. You see a lot of comments going on here. Okay, so we'll talk about comments first of all, and I'm going to run this fairly early on in a moment because I want to talk about variables and mutability. So comments in Rust are always done doing 2 slashes. You can either place them above the code being annotated. For more than one line you'll need 2, I'll put a row there, 2 slashes, funny, 2 slashes for each line. So it's not like in some languages where you have you have this additional form of commenting where you can have like start and end commenting. Obviously anything that's placed after the comment on that line is part of the comment. And you can see the other useful thing is I can put it at the end of a line as well. So we did see last week in the last episode how to basically, create a variable. And I mentioned that by default variables are mutable. Oh, did I say mutable? Immutable I meant. Sorry. Variables by default are immutable. Lucky I caught that. So, yeah, default variables are immutable, meaning that once they're set, they can't be changed. So, here you can see we haven't done anything special here. So, by default, x is immutable. We've assigned it the value 5, and then a bit later down we're trying to assign the value 6 to it. So let's see what happens if we run this program. So whoops, I meant to do, aha, did you see what I did wrong there? So what I should have done is cd variables. Now we're good because we're in a folder which has a toml file, so that's quite handy. Yeah, we won't do anything by accident, but I do need the cargo run command. Okay, so the nice thing is it's picked up. We cannot assign twice to an immutable variable. So how can we deal with this if we did genuinely want to change our value? So we have to explicitly tell it that we would like the value to be mutable in here for that to work. So let's try saving that and recompiling it and seeing what happens. And bit of a spoiler here, so you can see there's a whole load of other code we're going to move down as we go through different concepts. But the point is, it's run now because I've placed this in. So that's one way we can deal with that error, which is to say, okay, well, let's just make the variable mutable. Now, the other way we could do it, and we saw this in the previous episode, is we could not that you necessarily have to, we could make the variable, we could make it a shadow. So to do that, we have to do this. So how this works, in the first way we had it by adding mutable, it allows us to change the value that x binds to. In the second instance, which is what I've just changed it to now, I've removed that mute that I just added in a moment ago. Let creates a shadow of x to which we can bind a new value. But the other thing to think about this is think this through and think, what other combinations assignment of x that you could do might cause problems. So this is a good thing to have a play around with, is like, what if I do this and make this mutable, which means I can change it, or if I decide to shadow it, what are the advantages and disadvantages of doing that in my programming? Variables are immutable for a reason in Rust, and we'll probably dive a little bit deeper into that as we go through in later programs as to why we would keep that default setting on a variable. But in order to change the binding, we can do that in several different ways. And again, I think in the previous episode we saw how doing it this way by creating a shadow might be better ways of doing things, particularly, and we'll revisit in a moment actually again, if we want to maybe change the type of the value to something that's going to serve us better further down in the program. So if I do this now and make sure I save it, it also works. But if we now go back to how it was, that's how it was originally when I started this tutorial. Here you go, error comes back. So yep, a couple of ways we can alleviate that. For the purpose of this running, I'm just going to make that mutable. I've deliberately named things differently than in the chapters because I wanted to not get into a situation where I was reusing a variable name further down. So you might notice my variable naming conventions are slightly different than in the book. So other things that you'll come across in Rust that are always that are immutable are constants, and they are always immutable. You can't make a constant mutable. You can't use mut to change that. There's also a naming convention, and you can see it's all caps here, and we've got, because we're using all caps, we've got this underscore here to sort of make it stand out that it's a variable called max points. Also, another thing, you can use underscore if it makes numbers a bit clearer in terms of how they're split up. So you can see 100,000 here. I've got underscore there to maybe make that a little bit clearer with the value. Now, of course, if you've done programming before, you know why you want to use constants. It gives you a good way of having, say there's a value that you're going to reoccur over and over again and reuse in different places, like, I don't know, say a sales tax value or something like that, or some sort of weighting that you're using consistently. I've used it in programs where I wanted to set the default return values on, say, an API value on a function that I was using. So, somewhere early in the program, I might have, a constant for the total values returned. So if I then are using that further in different places in the program, I'm using the constant name, and then that way, if I need to change that number of values returned, I'm not having to go through everywhere where I've hard coded it if I'd done it that way by putting the actual value in. So this way, it's really easy to spot where you've used the constant. And that's not something that's unique to Rust. It's all over all sorts of programming languages, but it might just be enforced slightly different in Rust. And again, it's a good thing to understand when you're moving between languages, how what are the limitations of constants, or how are they handled, what conventions are used. And in this case, constants are always immutable, and you can't use mut to change that like we did up here. And there's also a naming convention that's commonly used. You'll see in here I've got a lot of print lns. Something really cool I've noticed in when you compile it is if you write like a variable name and you never actually use it anywhere, you don't do anything with it. So like if you define it or bind it, but then nothing is done with it, you get an error message, which is pretty cool. For me, that's a great way of actually picking up things like misspellings on variables sometimes, and then calling it something different in the program. So and of course you probably generate other errors through doing that, but I find that really useful actually, that it knows if you've not used a variable beyond the initial binding. So I found that if I had just done this here and didn't do anything with it, didn't try and print it out, I'd get an error at compilation time, or so. Below are more examples of using a let to facilitate shadowing, because I wanted to sort of also show you some more examples beyond the one we saw originally where we were changing the type. We might also be performing, say, like some sort of operation on a variable, and as a consequence we might want to shadow that. Equally, we could make let z mutable. That would be another way. But so again, you can just see here, I can shadow this once and shadow it again. I mean, I could just keep on shadowing it, because what it's doing is it's basically creating a brand new, brand new, even though it's called the same, but it's a new binding each time. Now, the other reason you'd want to do this, which is quite cool, is when you do it this way, if you use shadowing, and you'll see it here. So if we've got a value which is like let spaces equal a space, and then we decide that actually we want to change spaces to be the length of that space. If we'd missed out, so we did it a different way and we made spaces mutable by putting mut here and then just removed the let here, we'd get an error because we're now trying to change a mutable value to a different type. And you can see here, if I make the original let mutable and accordingly remove the second let, notice it creates an error. So let's try that. Let's try it if we were to do it this way. So with this way, we're not shadowing now, we're just we're just changing spaces. Let's see if this freaks out when we try and run it. And there you go. So it's not happy. So instead of finding a string, which is how we originally bound this was a string, it found usize, found a different thing. And we'll talk about data types in a moment as well. So again, just we do want this to run as we go down the code. So I'm going to change that back to shadowing instead. And now, here we go. There we go, it's working again. The only reason why I put these dashes in here, because if you remember a print command, you've got println, which is actually a print macro, not a function. And then the text I want to put in, the curly braces are the spaceholder, the placeholder. And then here is the actual variable we're going to put in the placeholder. I wanted to put dashes either side so you could see actually this was 4 blank spaces. That's all, as opposed to the number 4 there. Now, data types. So we've got scalar types, which are single values, so that's integers, floating points, booleans and characters. Now, if you don't stipulate a type, Rust will infer a type based on the value and how we use it in the program. So it will try and infer certain things. And you can see here, I can sort of force it so it doesn't have to infer. So, and again, we did see an example of this last week. So what I'm doing here is I'm taking, a variable that I've called some variable, and I'm saying, telling Rust that I want it to be a U32, a type U32. And it's going to take the value 42 in there. If I didn't do that and remove this, then what would happen is Rust would try and infer from this what some variable, the variable some variable might be in terms of its type. And there's a number of different types here that you can stipulate so it doesn't have to infer. I've made this table a little smaller so I didn't have to type it all out, but basically it starts off with 8-bit and the signed version is I8, the unsigned is U8, and that goes 8-bit, 16-bit, 32-bit, 64-bit through to 128-bit. And so, for instance, the 16-bit version would be I16 for the signed and U16 for the unsigned, and you've seen here the 32-bit. So that's how so the naming convention for this is pretty easy to work out. Once you know what 8-bit looks like, you can work it out, and just knowing that it goes up to 128-bit. There's also this, which is it defines based on the architecture. So I-sized is the signed version for whatever architecture you're on, and U-size is for the unsigned. And that's probably either going to be 64-bit or 32. Now, interestingly, the default integer type is I32. So if I was to do this without stipulating, it would default to I32 if it saw an integer there. Within the integer types, you can also have literals. So you can, this is 98,222 in decimal, so that there, as I said earlier, you can use underscore to make big numbers a little bit more readable, because if you used a comma in that, you could understand it would misrepresent, it would think it's something else. So that's why underscore is used. Obviously hex, you've got here 0x in front of the hex code. Octal is 0O in front of the octal code, and binary is 0B in front of the binary code. Then there are also byte integers as well, so you put a B in front of there, and then whatever the single byte character is there. So moving on to floating point types, you can obviously, again, Rust will infer based on what it sees. So if it sees this 2.0, it's going to infer that it's a 64-bit float. And again, we can stipulate so it doesn't infer. So here we've said, no, I want this to be a 32-bit float. So the default here, and again, I've just printed those out simply because I needed to use them so I didn't get an error when I was doing this. Boolean types, again, I've got an example of what it would look like if you just let it infer. So notice as well, I'm using the word true without speech marks around it, because obviously if I did when I use speech marks around it, it's text. So here it's a Boolean type, but if I really wanted to, I could explicitly state the type as I've done here. But you can see from the results I've got, doesn't matter either way, it's correctly inferred that just having the word true there. Same as if I'd not done this here, if I hadn't included this and just had false, it would infer that, yeah, it was a Boolean type. Then we have character types. So here, I just put it round. Single character with single speech marks around it, like a single comma there. Not a comma, yeah, single speech mark. Characters are 4-byte Unicode scalar values. So that stretches beyond just, the ASCII codes. If anybody remembers ASCII codes from back in the day, I can remember not learning them off by heart, but having having printouts of ASCII codes, because I think when I worked in certainly Commodore Basic, there was an extended ASCII table which also included various certain graphical characters as well. Now again, this is something that over time you'll get to know when Rust talks about characters, what it includes as a character. Obviously, it's going to be single characters from the alphabet, single numbers, things like punctuation marks and all things like that. But also that might also include other characters that can be produced from 4-code Unicode scalar values. And I believe there's a chapter later on we'll be looking at where they go into a bit more depth around this. Compound types. So Rust has 2 primitive compound types. There's the tuple, and there is the array. Now obviously, as we get on deeper into the language, you'll see that through the use of various other features in Rust and functions, there are there are extended compound types which can be built off of this, and we'll be looking at that, things like vectors, but not today. So tuple type. A tuple is a general way of grouping together a number of values of differing types into one compound type. In the following example, there are additional optional types. Notice the use of a bracket to contain the comma-separated values of a tuple. A tuple is a fixed length and can't grow or shrink once defined. So you can see here in this example, I have defined so that Rust doesn't have to infer. And again, notice once I start introducing this sort of syntax, have to remember here to include a colon after the variable name when I'm sort of binding it using a let command. We could leave that out and just let Rust infer them, So once you've got them in, how do you get them out? And so obviously there's going to be various ways programmatically of doing this, but there's a couple of relatively simple ways of doing this. One is to use what's called destructuring. So what you do is you basically create some new variables, and you bind them to the deconstructed tuple. So XX, YY, ZZ is now element 1, element 2, and element 3 of the tuple. And so you can see here, there we go. So that's destructuring. Did I say deconstructing? I meant destructuring if I did. So yeah, that's destructuring. Another is to access the element directly. So it's to use this dot here and then followed by the number of the index. Now, anybody that's programmed before will be familiar with how indexing works on compound structures and various other things, whatever they're called in other languages, lists, and will know that the first value, the first element in the vast majority of programming languages is zero index. So that's something you've got to get used to. It's not 1, it's 0. There are languages I do know where you can change that base value. I never do that myself because it's just too confusing for people that are used to seeing it the other way who programming. So yeah, I do like I said, in other languages I've seen ways of changing that base index. So yeah, index, the first value in an index is 0, the second value is 1, the third value is 2. So you just got to remember it's off by 1. So tup.0 returns the same value as if we'd destructured it, the first value, and then 1, a second value, and 2, the third value. And you can see, just here as proof, the values are identical. So that's very basically tuples, and we'll revisit those later on in this series. Then we've got array types. So with array types, every element must be the same type. We can't mix them like we can with a tuple. And they're fixed length again, so we can't grow or shrink once created. We'll be looking at vectors in a later episode, which can. Notice the square brackets that contain the comma-separated values of the array. You can also include an array type, again, if you don't want it to infer. Now, because they're all the same, the way you do that is slightly different than a tuple. You're using square brackets again for, it's nice that they're consistent here, but you can see here, I'm telling it that the values are going to be I32s and there's 5 of them. And there's a semicolon there separating the two. And again, if it's a form you've not seen before, you might get a little bit confused if it's a form you've seen. You've seen things been done different in other languages with arrays. So that's, I find often when I've moved between different languages, this whole area of compound types can be vastly different often. In some languages they're very similar, but in others, how you define them, if you've come from the world of original BASIC, you've got things like dim commands, like dimension commands and all sorts of things like that. Other languages will handle it differently. Now the other thing is this syntax is flexible in that there is also a way that you can use it to create multiple elements of the same value. So here I can use this, and what this will do is this will create basically an array with 5 elements in it, and all the elements are 3. Again, in this example, it's inferring the contents. So there, just so you can see, there's a couple of different ways of setting up arrays. in terms of both whether or not you choose to let Rust infer the type or not, and whether or not you want to use shorthand for where elements repeat themselves. Primarily you want to use an array for a collection that does not need to have an element added or removed. So the obvious choice is for things like an array containing months, 12 months of the year. That's not likely to change. Days of the week or work days in the week. And once you have that set up in a program, unlikely to want to change that. And again, I mentioned if there was a situation where you want to set up a compound type similar to an array, vectors are the place to go. And we'll be looking at that in a later episode. So how do you access array elements? Basically, you'll see here, if I wanted to access, say, the first element, again, there's several different ways you can get the stuff out, in terms of printing it. So one is to simply just bind it to another variable, as I've done here. So I've referenced this again with arrays with, our very first, our base element, the first element, starts at 0. So element 1 is, in this case, AR, open square bracket, 0, close square bracket. If I wanted the second element in the array, it would be 1, and so on. And you can see here I've done it both with this one and then months 1. And then down here I've printed them out this way, but also shown that you could just access them directly without rebinding them, or just binding them to their own variable. And here you can see it works either way. And why wouldn't it? So yeah, if you try to use an index value for an element that does not exist, so if here I tried to, so with this, if in the case of the months, my indexes are going to run from 0 to 11, because there's 12 months in the year, but I'm running from 0, or 12 months in my array, should I say. But if I try and actually put in 12 here, I'm going to get an error. So let's just deliberately break it. I haven't tried this yet, actually. This actually, bizarrely, I find this fascinating, this whole area of programming where what happens if you try and access an array that's outside of the range. Just fix that, and you can see exactly here index is out of bounds. So in this particular instance it's not gonna create a problem, because within the program itself I've set that index, so it was able to pick it up at compile time. And it gives us this warning where it's going. This operation will panic at runtime. Now, one area where this can come home to haunt you, and I think when I used to programming, there was an aspect here that was called defensive programming. So a lot of people are probably familiar with error trapping. So that's where, the program kicks an error up and you trap for it. And we saw that last week. There's a few things we used last week which do that. But what if the program causes an error as a result of someone putting in a bad value, and you actually want to catch that before that even happens? So that's where defensive programming comes in. So you might choose to, at your input stage, when you're input, say we had an instant where you ask the user to select a month, and they chose, and you gave them a list of numbers to put in, and you did the necessary calculation so they could put in, say, 12 to be December, and then you did the conversion to make 12 down to 11 for the purposes of your array. But suppose they decide to put 13 in. Obviously, if now in part of your programming it tries to access the 12th element because you've adjusted it accordingly, you know, 12th elements, the index of 12, it's not there because you're with 12 elements, your index runs from 0 to 11. So it's gonna kick up an error like this, but you don't want it to do that. You don't want it to get that far. So in your code, you would, you know, put in, you know, a warning if someone puts in, you know, anything that's not between, you know, 1 to 12 inclusive, or whatever, again, whatever value you're using to then subsequently reference an index, and then, you know, you've adjusted that value in the program. You know, you would want to, so you have something go back and say, no, you know, this isn't a valid input, try again. So yeah, so again, just something to think about in terms of when you are accessing arrays. Is there anything in the program that, I suppose the simplest way of thinking it, is there anything in the program either you've coded in or the user could present in which will cause your indexes to be out of bounds? And then what steps do you need to make to ensure that doesn't happen? You know, if it's a coding error, then obviously, hopefully in debugging, you pick that up. If it's something that requires defensive programming with when you're putting inputs in, then obviously you would need to add additional code to do that. So again, here, for example, as a result of unvalidated user entry, which selects a certain index value which is out of bounds for the array it accesses. And just wanted to finish off with the obvious. So obviously there's numeric operations in Rust. So you have addition, and most of this, if you work in programming languages already, you'll recognize some of these. No doubt we'll get onto various shortcuts like you see in C and its derivatives. But you can see here we've got addition, subtraction, multiplication, division, and then the percent symbol, which is used as doing for calculation of remainder. So you can see here. Actually, I should have changed that. I didn't. Yeah, those are the perils of. Actually, yeah, those are the perils of copy and pasting. Let me just do that. So might as well correct myself, even though it's not going to make a lot of difference here to the training. And again, one of the reasons why I wanted to put the prints in here is so I don't get warnings about me not using things. So this is a good opportunity to check and see if I've managed to spell those right, and if I haven't, we're going to get some errors. No, good. So yeah, and you can see as well here it's done this. Now, one thing we can experiment with here, what happens if we do this? Because this is always interesting, and I do encourage you to play around with stuff like this if you're curious as to how Rust handles divisions. So you can see here I've got 56 divided by 32. Now if I do this, let's try that. So essentially it's the same value. I've just introduced a decimal point there. And so what's happened again, from our values we put in, Rust has inferred what sort of result to kick out. So here what it's doing is, if I didn't have these, we're getting, it dividing one integer by another. So we're getting this, we're just getting the, just the whole number part of this. So, without the remainder. Whereas with this, when we got the 0 in, we're getting it, there's 1.75. If we take the zeros out, we just get that integer result. And there we are, of 1. So hopefully that's been helpful. It's probably, again, that the episode has probably run over long, but I just wanted to go through this obviously fairly slowly. If this is your first introduction to Rust, I do apologise to anybody that is an experienced programmer. This must be like pulling teeth. So, but anyway, such is the nature of this and the way I've decided to go through it. So yeah, I think next episode, I don't know which way round to do it yet. Whether I do functions first or not. I'm tempted to do program control first, actually, because then that might be better in terms of I can do maybe some more interesting things in when I get to talk about functions, if I've already spoken about loops and if-then statements and stuff like that. So thanks once again for watching, and bye for now.